The Energy Warden Policy Module is a web-based system for monitoring the real-time in-situ performance of different renewable energy devices installed in a building. These are photovoltaic, wind turbine, solar thermal, and geothermal devices. The Energy Warden Policy Module monitors also the performance of the building as a whole in terms of CO2 emissions. The Energy Warden Policy Tool functionality is based on existing international performance standards. These standards have been appropriately adapted for in-situ monitoring since these are usually meant for laboratory use. The user should first register his product by inserting the name, contact details, company name, the product serial number if it's available, and the password. Then the user should log in into the account. In order to monitor performance and various other operating parameters of a new system, either photovoltaic, wind turbine, solar thermal, or geothermal, initially the user should press the plant configuration button in order to import the plant data. Select the power plant type from the drop-down menu. There are 4 options: photovoltaic, wind turbine, solar thermal, and geothermal. Then press the New Plant button and insert the requested data. When you are finished with the plant configuration data, by pressing the button Sensor Data Import, the installed system should be selected from the drop-down menu, and the sensor data will be uploaded and imported to the database automatically. It should be pointed out that the Energy Warden Policy Module can plot a wide range of different charts, for example, area charts, bar charts, column charts, line charts, and 3D charts. Moreover, the Energy Warden Policy Module can plot results for 3 different pre-selected periods: the 7, the 30, and the 365 days. Also, there is the option of showing all the available data by selecting the option All Available Data. Finally, a specified period of time can be manually selected using the option Data Range. Solar Thermal Policy Module. The Solar Thermal Policy Module allows the monitoring of the collector efficiency, storage tank, heat losses, system utilization factor, and the CO2 savings. As mentioned earlier, the first step that needs to be done is to insert the system plant configuration data. Initially, the location of the system should be inserted, then the stored tank capacity and the absorber collector area. The maximum efficiency at the temperature difference between water in the collector and the ambient temperature equal to 0, the maximum temperature difference point and the efficiency at maximum temperature difference point should be added in order to plot the nominal efficiency curve of the examined system as extracted by the accredited laboratories report based on the European standard EN 12975. Then, the sensor data should be imported. For that reason, the power plant type and the examined plant should be selected. Using the Select Sensor drop-down menu, all measured values from sensors that are needed for the performance could be uploaded and imported to the Energy Warden Policy Module. The drop-down list contains the following sensors: tank cold water inlet temperature sensor, which is the water temperature of the cold water that comes directly from the city supply. It is used for the calculation of the system utilization factor. Tank water outlet temperature sensor, which is the temperature of the water at the outlet of the storage tank for user consumption. It is used for the calculation of the collector efficiency and the system utilization factor. Hot water consumption sensor, which measures liter per hour and is used also for the calculation of the system utilization factor. Temperature at 2/3 of tank height sensor measures the mean temperature of the hot water tank. This value is very important for the calculation of the storage tank heat loss coefficient. More specifically, the calculation takes into account the initial average water temperature and the final average water temperature for the time period of night when there is no drawn off of hot water. Electricity meter sensor that measures the power consumption for heating up the water. This value is used for the calculation of the system utilization factor. Collector inlet temperature sensor measures the inlet temperature of the circulating water between collector and tank. It is used for the calculation of the collector efficiency and the system utilization factor. Collector outlet temperature sensor measures the outlet temperature of the circulating water between collector and tank. For a sunny day, it could be 3 to 5 degrees higher than the collector inlet temperature. It is used for the calculation of the collector efficiency and the system utilization factor. The pyranometer measures the solar irradiance and it is used for the collector efficiency calculation. Finally, the collector flow meter measures the volume of water that circulates between collector and tank. It is used for the calculation of the collector efficiency and the system utilization factor. The last sensor is the ambient temperature. It is recommended that the sensor data mentioned before are measured every second and the average of these 60 measurements is recorded in the database. After the data importing, the graphs for each parameter could be plotted. By selecting the performance monitoring button, the graphical representation of each measured value can be shown. For example, the BRE Innovation Center plant is selected from the drop-down menu and from the measured values the collector inlet temperature. Then, as mentioned earlier, there are various chart types to see the monitor data. Area charts, bar charts, column charts, line charts, and 3D charts. Also, you can define the time period of the plotted results. With regards to the calculated values, if we select, for example, the collector efficiency, we can see a continuous line graph of the nominal efficiency curve as extracted by the accredited laboratories report based on standard EN 12975, while the measured values are illustrated as dots. The collector efficiency graph is used to represent the performance of a solar collector in various conditions. Usually, the peak efficiency value is used when the temperature difference between water in the collector and the ambient temperature is zero. However, it is very important to know the slope of the curve for various temperature differences between water in the collector and the ambient temperature. The slopes of the line in the graph represent their heat loss factors. The steeper the slope, the higher the collector heat losses. A line with a small slope represents a collector that loses very small amount of heat to its surroundings and has a very high thermal efficiency. The policy module plots the efficiency curve for a wide range of the temperature difference Tm minus Ta divided by G, starting from 0, the maximum efficiency, up to approximately 0.07 or even higher. This range of values covers both the situation with cold water in the tank for use during the next morning and also the situation where the water in the tank remains hot due to low consumption during the last evening. If the measured values are close to the nominal line with a small range with either above or below for different rates of Tm minus Ta over G, that means that the system operates in a very efficient way. If the dispersion of measured values is greater but equally spread, that means the system operates well. In that case, the wider dispersion is mainly related with the fact that the values are plotted as red. If the mean average of 60 measured values per minute is considered, then the dispersion is much lower. If most of the measured values are lower than the nominal line, a wide range of different rates of Tm minus Ta divided by G, that means that the system is not performing well, either mainly due to the increased system thermal convection heat losses or due to installation problems. With regards to the storage tank heat loss coefficient, that represents the heat losses during the night when no hot water is drawn off. The way the results are plotted is much clearer due to the fact that only one value is calculated every next morning. The storage tank heat loss coefficient is calculated by taking into account the density of the water, the specific heat capacity of water, the fluid capacity of the store, the duration of the cooling period, the ambient air temperature, the final water temperature at the next morning, and the initial average tank water temperature. As mentioned earlier, for this calculation, the system should remain out of operation during night hours when there is no solar irradiation. The measured values are compared with the nominal ones as given by the test lab report based on standard EN 12976 Part 2. If the measured values are slightly higher than the nominal ones, that means the piping system has bad insulation and thermal bridges. If the measured values are much higher than the nominal ones, then the storage tank may have insulation problems that existed during the manufacturing process. The system utilization factor represents the solar fraction, which is the amount of produced solar energy versus the consumed energy. This value varies according to the place that the system has been installed and operated. For a volume of drawn-off hot water around 85% of the storage tank capacity, a typical fraction for a Scandinavian country should be around 40 to 45%. For Central Europe, around 50 to 55%, and for the Mediterranean region, around 75 to 80% for the whole year. Finally, the carbon emission savings from the useful solar energy can be plotted. By pressing the reporting button, a full report of the results can be printed. Thank you for your attention.